Okay, we're going to take a look at chapter 3. Okay. And chapter 3 is the energy equation, first law of thermodynamics. And first law of thermodynamics states that energy cannot be created or destroyed. It can only be transferred from one form to another. Although we're going to look at work in simple systems, transferring heat across boundaries, internal energy of a system, whatever the control volume analysis and problem solution. Okay, so what type of control volume we have. Enthalpy and specific heats. Enthalpy being defined as, it's defined as the internal energy of the system plus the product of the pressure and volume. Okay, and then we'll look at some applications very briefly. Okay, we'll look at the energy equation. And from fundamental laws of classical physics, mass, momentum, and energy are conserved, okay? Which essentially means you can't create or destroy mass, uh, momentum, or total energy. But they can change form, all right? But the total quantity remains constant. So essentially we have total energy of system is equal to the mass times the summation of all the specific energies of the system, which you can rewrite as internal energy plus the kinetic energy plus the potential energy. If you pull out the mass, you can write it as like this, where these E is essentially these three terms added together. Or we can write it in this form where we have mass times internal energy plus 1/2 times the velocity squared plus g, gravitational acceleration, times z, which is the vertical position. Okay. So when we have a control volume where we have a constant mass, then essentially the equation can be rewritten like this. And if we wrote it as a rate, all right, so this is like a closed system, we would have any rate of change, or dE dt. Essentially, this is the rate at which energy's changing in the system is equal to any heat coming in minus the work going out. So typically this is just in minus whatever's going out. Okay, but this is for, when we have a closed system or essentially a constant control mass. Okay, so if we take a look at the previous equation here, this is when we had a constant control mass. And if we want to determine throughout the process, in this case between two times, we wanted to determine the total energy that was changed, or the total internal energy. Well, in this case here in the control volume, that is essentially going to be the difference between whatever it was initially to whatever it is in the final state of the second time. And that's just the difference between the total heat coming in minus the work being performed, okay, or the work out, if you want to say it that way. And then this is just comes from the Q comes from the integration of the rate, heat coming in, and the total work is just the integral of the rate of the work being done or going out. Okay. Now, if we took a look at our total energy equation that we previously looked at, you would find that if we wanted to find what it is initially compared to what it is finally, or the change in the total energy in our system, we'd have whatever change in internal energy, change in kinetic energy, and change in potential energy. Okay. Just one thing to be aware here. Q and W, of course, are accumulated transfer over the time function. So it is a function of the path being followed. That's why it's an integral, not just a constant value times time. Okay, so this is important. Pay attention to this. And essentially, what we're talking about for both equations, we're talking about the change in storage. Okay, and it's just the whatever's coming in minus whatever's going out. All right. Okay, so we're going to take a look at a piston cylinder that compresses a gas with piston work input of 200 kJ. The gas becomes warm at 45 kJ by heat transfer to the piston cylinder walls. and consider the gas as a control volume and determine its change in internal energy. Okay. So for this, we need a couple of assumptions. We're going to assume there's no change in elevation and there's no initial and final motion. Okay. We just assume essentially that it stopped in state 2. Okay. All right. So in that regard, what happens is when we write our energy equation, which is just essentially changes in internal energy, kinetic energy, and potential energy, which we already is equal to basically the heat coming in minus the work going out. Okay, with our previous assumptions, what we'll find is the kinetic and potential energy are 0. So then we just have this change in internal energy essentially equal to negative 45 kjoules, because in this case it was essentially reverse of what we had looked at, or when this equation was derived. We go back to this control mass or control volume. Heat was coming in and work was going out. Okay, so since this is just the inverse of that, we have a negative heat, and we have a negative for the work. Okay, and that just equals 155 kjoules. Okay, and that's it. That ends that problem. Okay, so the next problem, we're going to look at writing the continuity and energy equations for control volume as shown. Okay, so with this control volume, there actually are 3 storage places or 3 subdomains, okay, that are part of this. Okay, and some of the other things to observe. Work is out from here, from B. We have heat coming into C. We also have heat coming into A. Okay. For the whole system, we're not going to have any mass entering or leaving. So we can write our continuity equation, which essentially is it's a conservation of mass equation. Okay. Right, and that's going to be equal to 0 since nothing leaves. And what we can say is the change in control volume equals mass flow rate of A, B, and mass flow rate of C. And of course, since nothing leaves, the summation of these has to be equal to 0. And then the energy equation, as before, just we previously, if we write it in terms of rates, change in energy, control volume, essentially change in A, B, and C, which is equal to whatever's coming in, which is QA and QC, and whatever's going out. Okay, and that's what this equation simplifies to. Now if we integrate the instantaneous rates, we're going to have some like initial mass. So, sorry, here's the initial mass. The initial masses of the 3 added together, and here's the final masses. Of course, we know by the continuity, through continuity where we have no mass entering, leaving the control volume, that this is going to be equal to 0. And the same thing here. So it just has the initial energies and then the final energies, which is just going to be equal to essentially what we observed before, the total heat coming in at subdomain A, and C, heat coming in C, minus whatever work is being done out. And that is pretty much it. So these are the 2 forms of the equations. So the rate forms and then the finite forms here. Okay, we'll start with the first law of thermodynamics. Basic idea of first law of thermodynamics is that energy cannot be created or destroyed. You can only alter its form. Now, if we consider a substance like water in a steam power plant or piston cylinder system going through several processes that are repeated, we would consider this to be like a cycle, or that's some examples of cycles. So we could write our energy equations in that form. where we could apply this to a complete cycle. Okay. Now, one of the key factors here is that it's equal to 0. So basic idea, this would be like integrals over a closed surface, or a closed, I shouldn't say closed surface, a closed curve. So essentially what's happening is that, whatever net energy, or net heat, sorry, net heat is added to the system minus whatever work is done through one complete cycle, it'll sum to 0. Okay. So the cycle integral is just writing in. So this is like the total heat, done in the system or coming into the system, written like this, and then the net cycle work is just written like this. Okay. So essentially, what this says, if you rewrite this, put heat on one side and work on the other, you come up with a total heat, or the net heat is going to be equal to the net work. And if we put it in terms of rates, then it's the rate at which, or the net rate at which heat is coming into the system is equal to the net rate at which work is being done. Okay. Okay. So typical real cycles have 4 processes. You can think about like a car engine, a 4-cycle engine, as an example. So if we step back and take a look at what we previously had for the energy equation. So we have our cyclic integrals, okay, where the summation is going to be equal to 0 if we perform the integration over the whole closed curve. Okay. So if we perform the integration over each of the processes, what we'll find is that we have some quantities. In this case, it's the difference between the first initial and the second, and the second state and the third state, third and fourth, and then from the fourth back to the first. If you notice that these will cancel pairwise, meaning, here's E1, cancels out this one, E2 cancels this one, E3 and E4. Okay. Now, if we perform the same cyclic integrals on the heat and the work being done, heat and work being performed, what we'll find is we have the same idea here. Now we have, if we write it in this form, from 1 to 2, 2 to 3, 3 to 4, 4 to 5, same thing with the works. What we'll find is, of course, all of these minus these will result in 0 also. Okay. What they say is, in most cases with these 4 processes, you're going to find the summation of all the heat is 0, and the summation of all the work is going to be 0 also. So you could have it separate in this case. We're going to look at these some more in 9 and 10, chapters 9 and 10. Okay, we have an example. We're going to apply the first law of thermodynamics. We have a window air conditioner that absorbs 1200 watts of heat from the air in the room, and requires an electrical power of 500 watts as an input. Find the rate of energy leaving the unit to the outside. So this is a cyclic machine, and just repeats the same process over and over again. So one way we can look at this is thinking about it in terms of the net in heat rate of heat coming in. Net is equal to the rate of heat being absorbed from the room minus whatever is leaving. Okay, and what we'll find here, in this case, that's just going to be the whatever work is being done. Another way to look at it, and actually you can derive this from here, just rearranging this algebraically. But another way we can think about this one is, here's the rate of heat leaving, and that's going to be equal to whatever heat's taken out of the room, essentially, and the electrical power used to run the air conditioner. So if you add those two together, you have a diagram like this. I think it's pretty easy to see. This is what's coming in, this is coming in, and this is what's leaving, and that's equal to the total. Okay, so now we can summarize essentially the equations we looked at. We looked at the rate form for uh, energy, rate of change of energy in a control volume, um, just equals whatever heat, the rate at which heat is coming into the system minus whatever's work is being performed. The output rate at which work is being done. Okay. If we're talking about a finite um, amount, essentially amount of time, or between two time periods of finite time, we could rewrite the equation like this, which we looked at previously. And here's the left side of our energy equation. And then the right side, we had the Q and the W, right up here. Okay. Now we'll look at the right-hand side terms and how different situations and physical setups, and look at some possible energy transfers as heat and as work. Okay, now we're going to look at work, mechanical work, and three forms of it for now. We'll look at friction, spring, and gravitation, or gravitational. Okay, so we're starting off with force. Force of friction is a coefficient of kinetic friction times the mass times gravitational acceleration. If we look at it just to start with, our incremental part of work is just defined as force over some displacement. So in this case, the incremental work is just equal to, this is our force, and this is our distance. Okay? So if we're looking from one position to another, we can determine the work by performing the integration. And this is the result from that integral. The next is spring. And we're starting off with, like, this is our initial unstretched length. And then the difference between these two, so x would be like, so our initial one minus however much you stretched it, either positive, compressed it or stretched it from that initial length. This is our delta x, essentially. Okay, we could do the same things before. We have our incremental component of work is just equal to the spring constant times that difference dot times our little incremental change in length. Okay, perform the integration from positions 1 to 2, or two different displacements. We do that, it just comes out to be ksy. Well, we make the substitution here to make the integration a little easier, and then we have it, we change the variable integration to y. So now we have from 1 to 2, and for the integration, this is what we get, right, where we have this substitution. Okay, so it's like, so y1 is basically x1 minus x naught, and then y2 is x2 minus x naught. Okay, and the third one is gravitation, and this one is just mass times gravitational acceleration is the force, and then the work in this case is going to be just that force times the force. This is a force term, so the incremental portion of work is just equal to the force times that incremental displacement change, so vertical change. And if we do the same thing, we integrate over that, and we just come up with a difference in displacement. And this is also, we see this as potential energies. Okay, so we can define this as potential energy. Okay, and that's about it. So those are the three we're going to look at. Okay, now we'll look at power, and it basically comes from the work term, where now that we're concerned with, you know, work being performed as a function of time. So we have our incremental portion of work is just equal to F times that little tiny incremental displacement, right? So this is defined in the SI unit system as Newton meter. 1 Newton meter is the same thing as 1 joule, okay? So we'll make that conversion as needed. Okay, now if we're looking at power, power is the instantaneous rate of change of that work with respect to time. And if we rewrite it, it's just going to be F, force, times the instantaneous rate of dx dt. So in this case, if you have like a constant force, and dx dt is our velocity term. So it's just F times the velocity. And the units of power, 1 watt is essentially 1 joule per second, or 1 newton meter per second. This could be converted over to horsepower. And of course, if you wanted to convert it back, so this is our USCS units, to watts, you can do that. So 1 horsepower is basically about 735 watts, or 0.7355 kilowatts. Okay. We also want to look at torque, and could be work of a shaft. It's also another way to express it. But we could do the same thing here, where we're looking for power, and it's the same thing as what we've previously had, F, V, except now, we're thinking about like this velocity here at some point that would be like rotating around and around and around here, is just equal to the, this is our F times R, which is our displacement, times our angular velocity. Okay. Now, if you just substitute in for torque for F of R, you have torque times the angular velocity. Okay. And then the last thing we'll look at is the specific work, which is just to find work per mass. Right. Okay, so we can look at an example. We'll go to the text for that. Here's example 3.2. Okay, in this problem, I have a car of certain mass. It drives along with a certain velocity. And from that, we're able to determine that it has a kinetic energy of 400 kJ. Okay, and then it's find the velocity. Okay, so we can do that from the kinetic energy equation. And then if it's raised with a crane, how high should it be lifted? That the standard in the standard gravitational field to have a potential energy that equals the kinetic energy. Okay, so we have two equations. Essentially, we're going to use the kinetic energy equation and the potential energy equation. Now we're applying the kinetic energy equation. Essentially, we just algebraically manipulate this and solve for velocity. We're already given the kinetic energy, which is this 400 kJ, 1/2 m, and we're already given the mass of the car. So rearranging that comes out to be 27 meters per second. All right. So now we can use that information here, the potential energy equal to this 400 kJ, and we have a mass, we have gravitational acceleration. We just need to determine the height. So we rearrange the equation, just divide potential energy, or in our case, potential energy equal to the kinetic energy, is equal to mass, potential energy divided by mass times gravity equals h. So you just perform this operation. Yeah, the other key point to this is that we're in kJ, okay? So we have to make sure that 1 joule is a newton meter. So we have to make the conversion. That's being done right here, right? Okay, to convert to newton meters, right? The same thing is done here. Notice it's 400,000 newton meters, or 400,000 joules. Okay, and that's it for that one. Okay, now we'll look at work at a moving boundary of a compressible substance. Okay, and we start off as we did before. We have this little incremental piece. Part of the work is equal to force times some displacement. Okay. What we start off with is that force in this case is just pressure times cross-sectional area. Okay, and we have a cylinder piston type of a configuration, right? Well, we just recognize that area times the distance. This is just the volume, and it's just the little piece of incremental part of the volume. So we can to find out the work, total work being done from position 1 to 2, we just perform the integration over this, where our variable integration is the volume. Okay, and the result of this is just essentially the area under this curve. Okay, all right. So in this case, it's a function of the path. Okay, So the work from 1 to 2 is a function of the path. And for example, in one case, we could have positive work or negative work. If we're having a decrease in volume, so the delta is a negative value, then if that's less than 0, then we'll have negative work. Now, just comparing some magnitudes, okay? So going from like 1 to 2, and then maybe 2 to 1 back to 1, you'll see that if you're following following the path of A, it would just be the area under A. And then for B, if this was the path back, this would be the area under B. And if it was C, this is the path, then this would be the area under C. And you notice just in terms of the magnitudes that, B is larger than A. The magnitude of B is larger than A, going from 1 to 2. And then C is larger than B. Okay. Now we'll take a look at work in a polytropic process. And the polytropic process definition essentially says pressure times volume raised to the power n will remain constant throughout the process. Okay. Now, if we take a look at sort of the two extremes for n, what we can observe here is that as n goes to infinity, this is essentially a constant volume process. And the other, as n goes to 0, this is a constant pressure process. Okay, so that's just looking at it, the values of n, how it approaches the two constant processes. So we can, with this in mind, we can define the pressure is equal to this constant times v to the negative n, okay, or c over v raised to the n power. Okay, so we rewrite this just as we have before when we're talking about boundary work. Okay, and so we make this substitution in for p, and we perform the integration, and the integration comes out to be this c over 1 minus n v to the 1 minus n, and then from 1 to 2, the limits are from 1 to 2. And if you go work through this, where you substitute in the values for c, or substitute in the for the constant c with p, v to the end, and this is the result that you have. And then this just becomes v to the 1, or just v2, and then this is v raised to these two together, just be v1 raised to the first power, which is just v1. So here's the final form of that. And this is, of course, if n is not equal to 1. Right. So the integral is a little bit different if n is equal to 1. Right? So then when you do that, you have to do the natural log form of the integration. Okay? So this is the form. So basically, the two equations that come out for work are when n is not equal to 1 is this form, and then when n is equal to 1, it's in this form here. And that's pretty much it. Thermal energy comes from the substance whose molecules and atoms are vibrating faster due to a rise in temperature. Okay, so essentially the molecules have kinetic energy associated with them. Right, and here's an example. So you have 3 different types, and this shows you in a diatomic molecule. You have translational, rotational, and vibrational. Okay, so vibrational is moving back and forth, and this is like for 2 atoms. Rotational energy, and then translational energy. Okay, so in motion here. Right. So increased temperature corresponds to higher energy levels. So higher temperature, you have higher energy in the different forms. Energy is exchanged between molecules because of through their collisions, and then they transfer collisions transfer energy from molecules with more energy to those with less. Okay, what do we see it as? Basically, high temperature towards a lower temperature mass. So hot will exchange energy to a lower temperature mass through these collisions. Okay. Okay, now we're going to look at heat transfer. We're going to look at three different ways in which heat is transferred from essentially from one mass to another. We could do it by, first is by convection. This is due to some fluid in motion passing across a surface. So the heat will be exchanged with that fluid. The next is by radiation. And in this case, it's photons from electromagnetic radiation. Photons are used for emission and absorption of photons. So through the photons, essentially. The third is through conduction, where you have some physical contact between matter and solid, liquid, or gas without having motion. Okay, and describe that a little more further. Okay, so what we'll do is we'll look at, as an example, we'll have like this is a home with some insulation and some walls and a roof, ceiling, and inside wall temperature out. I'm sorry, inside walls over here, outside walls over here, and then heat is, traveling through the wall, hitting the wall and traveling through it. Okay. So first thing is we have a delta T, which is equal to the outside minus the inside, or we can write this as delta T is equal to like the surrounding environment minus the temperature of the surface. Here the rate at which heat is entering or traveling through from one point to another or being exchanged. In this case, we have both conduction and convection, okay? And this just talks about conductivity changes. So more thermal conductivity if you have the thickness of the layers is thin, if they're thinner, of course, if they decrease in thickness. The other one is that you'll have more convection, heat exchange through convection if the velocity of that fluid increases. Okay. And this one also if you're talking about all of the thermal energy, the rate at which thermal energy is being exchanged, it increases with delta T. So you have more thermal energy exchange with delta T and the surface area. So if you have a larger surface area, okay, and then the thermal energy is going to go from higher to lower temperature. Now the following shows the models for each of the types of heat transfer. The rate at which heat is transferred through conductivity can be equal to just essentially K times the surface area delta T over the length or the thickness, okay, where K is the conductivity, thermal conductivity of that surface. Okay. All right. The next is convection. And convection is just equal to the H, should be equal. H, which is the coefficient, okay, convection coefficient. And here is the surface area. And of course this should be an equals here, and this is the delta T term. So this is T infinity minus T of the surface. Okay, so here's the heat, is the convection coefficient. All right, then simple radiation, and essentially, this can be simplified down to radiation coefficient times the surface area times the change in temperature. Okay. Okay, so we'll take a look at an example. Consider the constant transfer of energy from a warm room, 20 degrees C, to a colder ambient temperature of minus 10 degrees C through a single pane window as shown. Okay. All right, so we have some additional information here. So let's see. Okay, so the glass plane has a thickness of 5 millimeters and with a conductivity of 1.4 watts meters per K, meter K, and a total surface area of 0.5 meters squared. So it has a outside wind, so the convective heat transfer coefficient is 100 watts per meter squared K. So the outside wind blowing, here's the convection coefficient, or convective heat transfer coefficient of 100 watts per meter squared K times K. And then with an outer glass surface temperature 12.1 degrees, we would like to show the rate of heat transfer to in the glass and the convective layer. Okay, so we've just applied the two equations that previously we had for conduction and convection. All right, so we make all the substitutions. Here's our temperature difference between the surfaces. Okay, 20, the inside, and the outside being outside surface being minus 12.1 degrees. And this is the actual thickness of our glass. Okay, we use the K, thermal conductivity K that was given, and we have the area here. So that comes out to be minus 1,106 watts. Okay, and the negative sign here is just saying, okay, the direction of the energy transfer. All right, and then from the outside convection layer, we have the rate at which heat is being transferred, and it's just going to be H, which is given as 100 watts per meter squared K. Just substituting in that, and then the A, we have the A, and then delta T as before, and then this is in terms of Kelvin. Okay, which, remember, if it's a change in temperature in C, it's essentially the same. Delta C is the same as delta K. All right, and then the direction of this is from the higher to the lower temperatures. That is towards the outside. Okay, so it shows you how just to apply those two equations with the given values.